This video covers enantiomers. Enantiomers are a type of stereoisomer that are not identical to their mirror image. Before we begin, it's important that we cover a few definitions, and these are words we're going to be throwing around all the time. The first is the term enantiomers. Enantiomers are a special kind of stereoisomer that are not mirror images of one another. So when you use the term enantiomer, you're referring to the relationship of two molecules to each other. That is, they are mirror images and they're not identical. The second term you should be aware of is chiral molecule. A chiral molecule is a molecule that somewhere on it has a carbon with four different substituents, or what's called a chiral center, or as you see below, a chiral carbon, chiral center, or stereocenter, all referring to the specific carbon on a molecule with four different substituents. Before we begin doing questions and problems with enantiomers, I'd like you to take a few minutes to convince yourself that you can see the following. Using your model kit, I'd like you to build two molecules that are mirror images of each other. You don't have to worry about specific substituents. You can just choose a red, blue, a green atom and a hydrogen and place them around a carbon and build them in such a way that when you hold them up to each other, they're mirror images. After you've done that, I'd like you to A, convince yourself that they're mirror images, and B, convince yourself that these two molecules cannot be superimposed on each other. In other words, that they're different. Okay, so here's what I mean. I want you to build a carbon, and you have four different bonds possible on any carbon. And I want you to build these molecules such that they're mirror images of each other. So what I'm going to do is I'm going to put a green reflecting a green. I'm going to build that first. So the greens are reflecting the greens. Hydrogens are reflecting hydrogens. I'm going to put a blue atom reflecting a blue atom. Building it this way, blue is reflecting blue, coming towards you. And last, I'm going to put a red reflecting a red. So we're not worrying what the substituents are just yet. Right now, we're just going to convince ourselves that we can see that these are indeed enantiomers of one another. So what I've done is I've built them such that they mirror each other. So these two molecules each contain a carbon center with four different substituents. The substituents are arranged around the carbon such that they're direct mirror images of each other. Okay. And the next thing is I want you to see if you can superimpose these two molecules on each other. So when you try to do that, what you'll see is that maybe you can get the hydrogens and the red atoms to line up, but when you turn it around, the blue and the green don't line up. The point here is that while these molecules are mirror images of each other, they're simply not superimposable. You can never get more than two of the atoms to line up, and the other two will always be incompatible and not lined up. When you are presented with these molecules, they're not always presented to you as exactly mirror images. So this molecule, I could take the one that's on your left, and I could turn it around and present it to you this way. And I could ask the question, what's the relationship of these two molecules to each other? You might not see it right away. So in that kind of question, what you need to do is build the model, build the one on the left and the one on the right, and then rotate it and convince yourself either that they're mirror images or that they're directly superimposable and therefore the identical molecule. All right, so here is a typical question. Identify the chiral centers in the two molecules below. So what we're going to do is we're going to look at each of these molecules and we're going to scan them carbon by carbon and identify whether or not they have a chiral center present at each location. So let's start with this first one. I'm going to scan from left to right. So we start at this carbon. This carbon, if you know your skeleton structures, is a CH3 group. Definitely not chiral. We're looking for a carbon with four different substituents. Then we move on to the next carbon. This carbon. It has something different on the left and right. It has two hydrogens, so definitely not a chiral center. Now this carbon. Well, if we look at this carbon, it's got a methyl coming down. Off to the right, it's got this carbonyl. Off to the left, it's got something different. And it also has a hydrogen. So this carbon right here has four different substituents, and therefore is a chiral carbon. And typically on my test you would be asked to identify it by circling all the chiral carbons. If you keep scanning the molecule, let's keep going because sometimes there's more than one, and we look at this carbon is double bonded to an oxygen. So this carbon, whenever you have a carbon participating in a double bond, it's not going to be a chiral carbon. We keep going. This carbon might look visually to be chiral, but it's not. If you look at it carefully, it's attached to a CH3 group below, but also the rest of the parent molecule, this is a CH3 group as well. So this is not a chiral carbon. Now let's look at the molecule below. Well, I've already identified where the chiral center is right here. This carbon right here is chiral. If you look at it, this part of the ring here is different than this part of the ring below, and it's also attached to a methyl here and a hydrogen, which is not shown. 4 different substituents, therefore this is a chiral carbon. If you scan each of the other carbons in the ring, this one, this one, this one, and this one, these all have 2 hydrogens and are therefore not going to be chiral. This carbon right here is participating in a double bond with the oxygen, therefore is not chiral. Here's another type of question. Sometimes you're asked, what is the relationship between these 2 molecules? I'm going to give you 2 sets of questions. This first one, where you're asked, what's the relationship between these 2 molecules? And they're actually enantiomers. And then another question, you're also again asked, what's the relationship between these 2 molecules? And these are actually identical, or they're the same molecule. Okay, so the way I would begin to answer this question is I would start with the structure that you're given. So you're given these 2 structures, these 2 molecules, and you're asked what is the relationship between these 2 molecules. So what I would do is I would just simply build each molecule. I would build it this way, such that I'm holding it by the methyl. I'm going to make the red atom, I'm going to make that an ethyl. It's just easier to visualize. I'm making the green chlorine, and the hydrogen is a little gray ball. So I've just built the model exactly like the figure is on the piece of paper. Chlorine going away, hydrogen coming towards you, ethyl in the plane of the paper, methyl also in the plane of the paper sticking straight up. Okay, I'll put that one down, and I build the other one exactly like I see it. So I build this one exactly as I see it. Again, in this case, the chlorine is coming towards you and the hydrogen is going away from you. Okay, so now that you've built them the way you see them in the picture, you're free to rotate them in 3-dimensional space. So the first step is to build it and convince yourself that you've built it correctly. And now you're free to kind of play with it and see. And what you're looking for is you're looking for either that they're completely superimposable and therefore identical, or that you can line them up in such a way that they're mirror images. Now these happen to be mirror images so that I know that these guys are enantiomers. And that's why the first question, the answer was enantiomers. If you look at the second question that I gave you guys, it was this one. You couldn't necessarily tell just by looking at it which it was. So again, what you're going to do is you're going to build them as you see them, and then you're going to ask the question, how do these 2 things, how do they line up with each other? So I'm just going to rebuild them as I see them, just to save time. I'm going to go ahead and do that. And so I can't necessarily tell by the way they're drawn, but if I build them correctly, I can kind of play with them. And I ask myself, well, are they mirror images? Or, and I look at these two actually are completely superimposable. When I line them up, the methyls line up, the hydrogens line up, the chlorines line up, and the ethyl groups line up, which again, the ethyl I'm just showing with a red atom just for simplicity. So therefore, these molecules are identical molecules. So here's a third kind of question. You're given the structure of a molecule with a chiral center and you're asked to assign R or S configuration. In some cases you're asked to give the complete IUPAC name, or sometimes you're just asked whether or not it's R or S. So in order to assign RS, we need to review the ranking system. So what we do is we look at the atoms that are directly attached to the chiral carbon. and we assign the highest priority to the atom with the highest atomic number. So we look at the first atom out. The higher the atomic number, the higher the priority. Then, if the atoms attached directly to the chiral carbon are identical, for example, if there's 2 carbons, you go to the next atom. Double bonds are the equivalent to 2 single bonds. So, for example, a carbon-carbon-oxygen bond would be the equivalent of a carbon bonded to 2 oxygens. Next, you're going to assign priority. So, for example, in this one, you're going to look at the atoms that are directly attached to the chiral carbon in the center, right here. And you see that we have a hydrogen, a chlorine, a carbon, and a carbon. Well, chlorine of all these 4 has the highest atomic number, so it gets priority number 1. Of all of these, hydrogen has the lowest atomic number, and so it actually gets the priority of its 4th ranked. Now, the tricky part comes with these 2 carbons. So the carbons are identical, so now we need to go to the next atom out. Well, if we look at the carbon with the alcohol on it, it's attached to 2 hydrogens and an oxygen, whereas the carbon with the 3 hydrogens has a lower ranking. The reason is that 2 hydrogens and an oxygen is ranked higher than 3 hydrogens. So now we have our ranking in place. Once we have the ranking in place, we place it or we draw it with the lowest ranking substituent going away from us. Now this one was easy because it was already drawn that way for us with the lowest ranking substituent, the hydrogen, going away from us with the dashed lines. The next thing we do is we draw an arrow, almost like a steering wheel, going from 1 to 2 and then 2 to 3. If the arrows are moving in a clockwise rotation, then we say the configuration is R. So the answer to this would be it has the R configuration. What do you do now if the lowest priority is not in the back? So for example, you're asked to assign an RS configuration to this molecule. Well, we can assign priorities. The chlorine is the highest, the ethyl is second, the methyl's third, and the hydrogen is fourth. But we need to redraw this such that the hydrogen is going away from us. Because the way we're looking at it from this angle, it looks like it should be S, but it's actually not. So you have 2 choices here. You can either imagine that you're looking at the molecule from the other side and ask what direction would it go, or you can build the model, turn it around, and redraw it with the lowest priority in the back. When you do that, you'll see that it's actually R. Okay, so here's what I mean in the last question. The way the problem was presented to you, you were given this structure. You were given a molecule with the lowest priority coming towards you, the hydrogen. And you actually had, again, I'm saying the red is going to be an ethyl. You had the ethyl going to your right, the methyl going up, and the chlorine, which was actually the highest priority, was going away from you. So from the position that you were looking at it from, you were actually, what you were seeing was, it looked like it was S. But you're actually looking at it from the wrong side. You're looking at it from this side when you really need to be looking at it from this side. So this is why I recommend that you build the model like you see it on the paper, and then you turn it around and you view it from the other side. So if you can't imagine it from the other side, what you're doing is building it and turning it around. So now when you're looking at it with the hydrogen going away from you, you're seeing it from the correct perspective. And now what you're going to actually be seeing is, if we look at it this way, is actually going to be an R configuration. So that's why you have to not only know how to assign priorities, but you also have to orient the molecules such that you have the lowest priority going away from you.